Hello and Namaskar. Welcome to today's presentation Introduction to Contex Orthokeratology. Sorry for the initial delay and glitch. Uh, so today we have Steve Ernst from USA, California. Uh, I'll introduce Steve. He is the president of Contex. Started his contact lens career in production department of contact lens in Contex 1988. Having a mechanical engineering background, in 1992 he was certified as a master technician for CNC micro level lathes. He obtained his qualifications as an optician's certification in 1993. He has since become a master optician. In 1998, Steve played a major role in obtaining the first ever FDA approval for the contact lenses with an indication of orthokeratology. In 2012, he received the American Academy of Myopia Control Outstanding Achievement Award in recognition for development of the first orthokeratology lens designed for hypermetropia, presbyopia and astigmatism. The ContexOk E-system is Steve's most well-known achievements. By recently, he finished development of OKEX design for myopia management and improved refractive stability through variable optic zones diameters. He is also head of consultation and R&D department for Contex and specializes in hard-to-fit GP patients that includes orthokeratology, keratoconus, post-surgical, aspherics, and GP multifocals. Steve is a member of American Academy of Myopia Control. Now let me introduce myself also, because last time I forgot to introduce myself. So, of course, I'm Chandrashekhar Chawan, optometrist and ocularist serving the world since 3.5 decades into innovation, teaching and training. Diploma in optometry, PhD in physics from University of Mumbai, fellow of Scleral Lens Society, USA, inventor of diamond and gold contact lenses. As an eye jewelry, invented techniques for painting RGB scleral lenses, introduced modern ocular history and scleral lenses and orthokeratology in India. Orthokeratology and myopia control was introduced by me in India in 2004. Introduced ARC multifocal soft contact lenses and ARC Myo Vision and Astivision spectacle lenses, that is for myopia control spectacle. Holds multiple patents in various fields, practicing orthokeratology since 16 years, practicing in Mumbai as well as in Orlando. So today I am going to introduce you with the what is orthokeratology, just a basics, so that Steve can concentrate more on practical aspects of how to fit Ortho-k lenses. So orthokeratology is basically like okay, it's like molding the cornea. It's a temporary, like you do molding for the teeth, it is called orthodontistry. When you wear a ring in the fingers, if you remove it, you can see the impression of that ring on the finger. So similarly, on the same principles, what we are trying to do is change the shape of your cornea when you sleep. So it is overnight orthokeratology. So you wear these molds in the night, go to sleep. So what happens is, because of the push and pull, here it is pushing and here it is, there is a negative force that is pulling, the shape of the epithelium changes like this, and it creates a virtual lens, or it corrects the refractive error, refractive component of cornea, and you can see. So there is a difference between regular orthokeratology and Ortho-k lenses for myopia control. Basically it's a pupil dependent zone that Steve is going to explain, but in short, in myopia control we have to have a smaller pupillary zone, and for a regular myopia correction, that is larger optical zone. So usually it works up to -8, but at specialized designing it can go up to -12, -15 also. There are orthokeratologists like Nitesh, Marino Fermenti, and so many others, Matthew, Rob, Thomas. So they can correct up to -13, -15 also, because they play with the designing aspect. In normally it can be corrected up to 1.5 with the rule astigmatism and 0.75 against the rule astigmatism. But with the latest technologies of toric orthokeratology, you can go up to -3, 3.5 diopters of cylinder also. So what you need is basically a full correction. A topography is must. Without topography you cannot practice Ortho-k, because you are molding the corneal shape, and you should know what you are molding to, if there is any troubles, any troubleshooting or any problems later on. Tear film analysis has to be done. The eye has to be normal. You cannot perform this Ortho-k on a dry eye patients. For that you can check Shermer's tear breakup time and biomicroscopy. And these are the contraindication: keratoconus, ocular surface disorders, corneal ulcers, infection, pellucid, Terence, tear film disorders, and dry eye. Don't try to do it. There are certain people, exceptions, who can do Ortho-k on keratoconus patients as well. Of course, if you can't do Ortho-k, there are different modes to correct, that is spectacles, contact lenses, RGP, and later on when the child is adult, after 22, 24, once the cornea, the refractive error is stabilized, you can go for LASIK. In general fitting process, we have to call patients 2-3 visits. So first week, as soon as you give the lenses to wear overnight, the patient has to wear the lenses minimum 6 hours to get the effect of at least -3 diopters of correction in 6 hours. In the morning, patient will see everything clearly. During that first 2-3 hours, if you check him, you will get a fair good idea whether you are going on a correct direction. Then you call him after 1 week, again do the topo. You will get an idea whether your correction is correct, and then you can follow up after 1 month and 6 months, like that. So this is how the lenses looks like. Usually they are color coded, yellow, red, or green, or blue, just to identify between right and left. So there are a lot of companies in the market, but the leading companies are ContexOk. As you heard, he is the first one to get the FDA approval. Then there is a Paragon CRT, then there is a Euclid, Emerald, B Retainer, Dream. There are so many other companies also in the market. So basically what is happening is, because of the pressure on the epithelium, there are centrifugal forces that plays into action, and it shifts the epithelium on the periphery, and that change gives us the desired curvature change on the cornea. So this is the first curve, that is a base curve we call it, that acts on the center, that is the major change for the visual correction. Second curve is to hold that whatever is shifted, that goes into that reverse curve, and those cells gets holded up there. So that suction effect. So center there is a push, and periphery there is a pull. Then the third curve is usually for the bearing, so that the lens is centered all the time on the cornea. For that, of course, the diameter of the lens is also important. The HVID, that is horizontal visible iris diameter, minus 8% of that is the diameter of your Ortho-k lens or mold. So fourth curve is again peripheral curve, that is this is in general I am telling you. When you design, there are more than 6, 7, 8 curves as well. When you have to go for a higher correction, you have to add more curves. Second important thing is a good candidate selection. You cannot select a candidate with -8, -10 to start with. Select someone who is less than -5. It is best for the myopia control program, because most of the kids that you get is in the range of 1, 2, or 3. Catch them early so that you can control the myopia progression at a faster stage. but in general you can correct whatever you want up to -8 or more. Astigmatism, as I said, 1.5. The uh, the pupil diameter also is more important when you are giving a successful fit for the Ortho-k. Especially myopic patients have a tendency to have a little dilated pupil. So you have to consider that when you are designing or ordering the lenses. So when you order the lens, you have to mention the pupil diameter, because that is the success. If you give a Ortho-k lens to a normal patient who's in the evening he's going to drive home or drive around, and if your optic zone is less than 6 mm, he is going to get halos and disturbances in his vision. Whereas in children you want to have the smaller optical zone or treatment zone, you can say. Children usually don't complain about this halos and glares. That is my experience, because anyway they don't drive in the night. So patient selection is utmost important. If it is a limbal to limbal astigmatism, it's very difficult to correct, but with toric designs that also can be addressed up to certain extent. So read the topography, understand what kind of cornea you're dealing with, and then go ahead with the treatment. As I said, if you have irregular cones like a keratoconus or any other ocular surface issues, patient has already undergone some surgery or anything, you have to be careful while selecting this type of candidates for orthokeratology. I am not saying no, but you have to be expert to do that. Of course, you have to measure a standard IOP, do dry eye test, HVID, pupil diameter, etc. in the initial examination. This is how the lens usually looks like. There is a base curve, then fitting zone or reverse curve, alignment curve, and a peripheral curve. These are the basic curves, and in alignment curve there are multiple other curves involved depending on the power of the lens or the stability and the toricity of the lens. This curve has more curves when you actually design the lens. So in the follow-up, again you have to do topography examination to understand what is happening, do the best corrected visual acuity, do you need any correction or not. Usually the Ortho-k lenses comes with some power inside, that is called Jessen factor, plus 0.75 or plus 1 or plus 1.25. So the company will tell you what power it is, or you can check it under lensometer and you know. So any power you are correcting, the lens, Ortho-k lens has a fixed power on that, because it does not correct with the power, it corrects with the base curve. So you understand that, and do the follow-up, do the overcorrection. If there is, you need overcorrection, that means something is wrong. When you do the overcorrection, it should be plus 0.75 or whatever is the Jessen factor in that lens. When you remove the lens and do the correction, usually you will get a no overcorrection. So second important thing is you have to learn how to look at topography maps and what to make out of that. So axial maps is more important, tangential maps are more important. So you understand and learn how it is. I am going to give you one link to go online and check and learn how to read and understand these different maps. There is something called subtractive map. So this is the first map on a virgin cornea, and then you put a Ortho-k lens, and that topography map you subtract from each other and you will get something like this bullseye. So if you get this, then your correction is perfect. This is how the fluorescein pattern looks like. It's a flat, this is ideal fit. You have to have a central touch, there is a peripheral pull, and then again a touch. This is too steep. So I'll just give you 3 or 4 understanding. This is Smiley Face. When the patient was wearing the lens and sleeping in the night, the lens was going up, because when you examine the patient, you are not going to see this type of lens going up or down, but in the night the lens is going to look right up, down, or sideways. So with the topography you can make out what was happening in the night. So if you get a smiley face, that means the lens was riding high. If there is a central island, that means lens is too steep. frowny face, that means the lens was riding low. This is what you are looking for, bullseye. So you have to look for the bullseye pattern. If everything is correct, you will get a bullseye topography in a subtractive map. So it's a clinically proven procedure. Non-surgical, that means it can be corrected again. Once you feel, oh, it is going up or down, you just stop, ask patient not to wear the lenses, and after 1 week, that is called washout, and again you can start. So it's a reversible procedure. So no harm is done, easy adaptation, and it is overnight. So the child is, suppose if you are doing it for the children, the child is under the supervision of parents all the time, because the parents will be putting the lens in, or the child is putting the lens in, doesn't matter, but it is in the house. When he goes out, he is not wearing any glasses, no contact lenses, he is full of confidence, and nobody bullies him in the school. So no need of wearing the lenses during the daytime, but if required, it can be used in the daytime also. So when you order, you have to give full correction, K1, K2, HVID, best corrected trial lens that you use, topography readings, and you can, in India, this Primex Enterprise are the dealers for Contex. See, this presentation is not a commercial presentation, but this is to help you get started. So I am giving you practical tips, and actually the names and companies where you can actually order and start doing practicing orthokeratology. So Primex Enterprise llp@gmail.com, where there you can send all this information. You have to have a certification in orthokeratology, and that is very easy. You can go on orthoklens.com, and there is a section called Doctor Certification, and which is free. You can just go online. They will teach you. There will be some slides which will show you all the specs of this, and then there will be questions. If you answer them correctly, you will get a certificate. If you have a certificate, then only these people will give you the lenses. Just because you order the lens, they will not supply you. So you have to show at least once initially that you are certified. If you want a hands-on training at shekharai.com, you can inquire. There is a 2-day hands-on training for the optometrist or orthokeratologist or ophthalmologist to become a trained and certified orthokeratologist. So basically, in myopia correction, what it does, it gives this reverse zone gives a myopic defocus in front of the retina, and that sends the signal to the brain not to grow the eyeball, or puts a brake on the growth of the eyeball. So that's how the orthokeratology lens works in myopia control. We have been doing Orthok, but only in last 10 years we realized that it works for myopia control on this principle, and that's why we started making a smaller and smaller optic zone to get a perfect peripheral defocus, a myopic defocus for the kids to control the myopia progression. Randy Kojima is a fantastic optometrist at Pacific University, and he has a very lucid way of teaching topography. So go on this YouTube link and check for Randy Kojima, and you will learn everything about topography. He is a fantastic guy. Then get certified in various aspects of myopia control. May it be multifocal soft lenses, orthokeratology, spectacles, and confidently practice myopia control, because as you know, the world is almost 50% of the world will be myopic by 2050 by one of the study. So you have to be ready with all the knowledge, because you are the first point of contact with your patients, and you have to guide them correctly and properly. These are my references. So if you need anything to ask, you can write to me at shekhar@shekharai.com. Now I am going to invite Steve Ernst to talk about Contex Orthok. Let me change and get Steve on. Okay, I'm making Steve host so that he can share. Steve? Steve, we can't hear you. Something wrong with Steve's audio. Try adjusting your pin in the computer. No, Steve, we can't hear you. Okay, try speaking.
Can you hear?
Yes, I can. Yeah, we can hear now. Yeah, can go on. Steve, we can't hear you. Your microphone is not connected. No. Steve, try to adjust the pin in the computer. You muted yourself. Unmute. Steve, you have to unmute yourself. Yes. No. Your microphone is not connected. Yes, now try speaking. No, it's gone again. Sorry, Steve, we can't hear you.
For example, if you are buying a trial set from us and then you are placing the order, then it's 1 + 1. So you pay for one lens will be from our side. And the second offer is like if you are going for an empirical method, if you are placing an order for Contex lenses, then we'll provide you 20% discount.
Wonderful, Preeti. That is really good that we have some.
We start at the beginning?
Yes, please.
Okay. So, Contex, we've been around. We're a full-service RGP laboratory. We have over 40 years of experience with orthokeratology, and we consider ourselves to make the highest quality lenses in the industry. We've been in business since 1962, and we have 5 patents on orthokeratology, and we received the first FDA approval ever for Orthok-k. Nick Stoyan started our company back in 1962, but in 1984 he invented the first orthokeratology lens called the OK lens. Here he's receiving his AAO Founders Award back in 2010, and you can see we've received many other awards for our orthokeratology designs. At Contex, we have a doctor support and education center where we train doctors to fit Ortho-k lenses. And as you can see, we offer a certification program. You can go to oklens.com and get certified for the lenses. The OKE system design has been around for over 15 years. It's the workhorse design for standard orthokeratology up to about really 7 diopters. The OKEX design is really our myopia control, myopia management design. And then we have toric options for both those designs. We also make hyperopic lenses. The topography map there on the screen is actually a -6 diopter patient using the Medmont 3D graphic. The E system is based on eccentricity. The E represents eccentricity, and eccentricity value is the rate at which the central cornea flattens towards the periphery. You can see the more elliptical it becomes, the higher the E value. And that's the basis of our design. We developed this corneal model using over 600 topography maps. We analyze those maps and develop the corneal model that we build the lenses on. We don't have a fixed configuration for the zones and the radius values. We actually adapt them to the corneal model based on the shape and myopia reduction. Our alignment zone, as you'll see in the next slide, basically this shows your basic design where we have a base curve, a reverse zone, an alignment zone, and a second alignment zone. That's the E system design. And it's so simple that we just use the flat K reading, the refraction, and the E value to come up with our design code. So in this case, this patient would have a 43 flat K with a -4 refraction. This is just showing how we adjust the fit based on E value or flat K. And it's really quite simple. Each 0.1 E value represents approximately 20 microns. Our alignment curve is built on the corneal model, and it has an even tear film throughout. You can see that we adapt it here and adapt it here to the cornea so that we get a good centered lens. We also have 4 fitting methods. You can fit the lens either empirically, diagnostically, which is recommended, and you can also have a dispensable inventory set. And then recently, we've added our lens to the Medmont topographer where you can automatically fit the lens in there. This is just a simulated fit of the E system inside the Medmont, where we have applied it to an actual corneal topography map. You can see this is a good fitting lens by looking at the tear film below. This would be a loose fitting lens where we have minimal tear film in the center. And then this would be a tight lens or steep lens where we have too much tear film in the center and we've got a central vaulting going on. So those are just some samples of the simulation. One of the things, really, especially being international, the inventory sets can save a lot of time and increase your first lens fit success rate. Empirically, especially with the distance, it can be difficult to get a good first fit every time. The inventory systems actually come with a software program that helps you select the best lens out of the set. This is basically how the inventory program would work. It has a primary lens, which would be this 43-4, and each sequential lens up is looser and down is a little tighter. So very, very simple fitting. The ideal fluorescein pattern, Chandra covered, so I don't think we need to get into that, but that is what we would consider a good fitting lens right here. This next lens is going to be, I believe, that's a good fitting lens again, just centered well, right on top of the cornea. Now this would be what I would call a loose lens, where the lens is breaking away from the cornea and sliding down. You can see the little air bubble right here in the areas of clearance. Also notice that the central bearing is very dark, darker than the alignment zone. So that's a good sign that the lens is too loose. This is actually would be a tight lens. With a lens like this, you can see we have dimple veiling in the center and a very dark alignment. You notice the alignment zone is darker than the central bearing. And with this, we need to raise the E value or decrease the sagittal depth of the lens. We developed a fluorescein grading scale to help new doctors analyze the fluorescein. So first, we think it's important to look at the alignment zone and analyze that zone. Then you want to analyze the central zone, and finally, the reverse zone. You can see the grading scale down here where we have 5 pictures. So it's a 1 to 5 grading scale. And this grading scale works with this refit form. And we can get you those tools through Pretty. You can get those for you. We did a test group on the E-system lenses, and we had 65 patients where we reduced an average of 4.67 diopters. The myopia ranged from -0.5 to -825, and the average lenses per eye was 1.35. Our second group, we did 80 eyes with -4 diopters or less. And if you can see, you see the average lens there was 1.07 lenses per eye. So 74 out of 80 lenses only 80 eyes only needed 1 lens. When we go over 4 diopters, you can see the number jump to 1.84 lenses per eye. So the more myopia you treat, the bigger chance there is you're going to need a second lens for that patient. To summarize, OK E-system lenses can reduce up to 6, even 7 diopters of myopia, but accurate corneal data and topography are a must. We suggest that every doctor calibrate their equipment before they start orthokeratology. So that's a brief introduction on the E-system. If everyone wants to go get certified, there's more details in our certification test. Now we're going to discuss our toric option, the TAC we call it. What the toric axis does is it allows you to put an alignment curve here and a different alignment curve here for astigmatism so that we can balance the lens. We even have the capability to do multi-axis where we can change the alignment curve every 90 degrees and adapt the lens to the cornea almost exact. You can see in this image, we're just showing what the machines can do and what our software can do. We can cut an optic zone with 4 different radii within the optic zone. Each quadrant can be specific. Very high-tech stuff. The different configurations that we have for the toric lenses is a straight toric alignment zone, a toric reverse and alignment zone, and then the multi-axis design with a toric optic zone instead of toric alignment zones. You can see here, I'm showing a cornea that's very irregular, and you wouldn't want to start fitting with a patient like this. This is an example of what we can do with the toric lenses. You can see that down here in this quadrant, the cornea is very steep. Up here, it's fairly normal. And then over in here, these 2 quadrants are pretty similar. So with axis 0, we're using a 4162 with a 0.4E. With axis 180 over here, we're using a 4162 with a 0.6E. So we have about a 40 micron difference in the shape of the lens from the temporal side to the nasal side. And similarly, at 90 degrees up top, we're using a 0.5E, while down at the 270 or 6 o'clock, we have a very low E. So this is fairly complicated lens, but it demonstrates what we can do with the toric lenses. Here we're trying to show the difference in the sagittal heights. You can see from 1.974 all the way up to 2.081, that's a difference of 100 microns. And that's what we can do adapting to the cornea. You can see a pre-map and a post-map, and within a regular cornea like this, to be able to have a decent molding like that is pretty amazing. With a symmetric lens, there's no way you could fit a patient like this. This is a graphic that shows the basic design. And what we do is we try to apply more pressure. The blue area shows the flatter area of the treatment zone where we're applying more pressure to the steep meridian in order to reduce the astigmatism. The red area would be the standard base curve right there along the flat meridian. So we're assuming this is with the rule astigmatism. The pre-data for toric Ortho-k is very important, and we suggest looking at elevations. E values equal elevation. And you can see this is the same topography map, the same cornea, but here we're looking at an axial power view at the bottom, and up top we're showing the elevation changes. You can see the blue areas are really dropping off because of the steep area. But most topographers will give you an elevation value. Only the Medmont allows us to get the exact elevation at any meridian. And we like to pull those elevations at the chord diameter of the lens, which is typically 9.6 on an OKE system and 10.0 on an OKEX. It's very important when you take topography maps that you get a good round image. It's so important to get the eyelids out of the way and get a very good round map. Otherwise, if we don't have a complete map, we really can't design the proper lens or even fit the proper lens. This is an example of central astigmatism on the left and limbal astigmatism on the right. Chandra mentioned that limbal astigmatism is more difficult to reduce, but really with our designs and being able to utilize our multi-axis, we don't have any problem reducing limbal astigmatism anymore with our toric designs. It's actually easier, I think, now than central astigmatism, because with central astigmatism, you're only able to use one alignment curve and the lens will rotate on the blink, so you don't get a precise molding on the steep meridian. Here we're just showing, again, central astigmatism. You can see how symmetric the peripheral cornea is on this one and this one. So, you know, toric alignment curves don't work well on central astigmatism. I don't want to spend too much time on this because we had some technical difficulties, but you can see again here, this is a limbal astigmatism cornea where you can see the peripheral cornea is very different and the toric alignment curves will locate themselves there. This is an example of going through a toric case study. And we can get everybody this PowerPoint presentation. I can send it to Priti and she can forward it to you so you can all see this. This shows a standard Ortho-k lens, and what we're seeing in the bottom picture is a nice fit horizontally, but because of astigmatism you can see it lifting up. And really, once a toric lens is fit correctly on a toric cornea, it should look like the top picture. So it should look like a standard lens. You can see here we're using a toric alignment curve. It's still a little loose, but you can see how we've gotten rid of that clearance and laid the cornea down now, laid the alignment curve on the cornea. So the toric lens could be a little tighter here, but if you're too tight vertically, then it causes, uh-oh. Did you lose the presentation?
No, we can see.
Okay, I lost it. It flashed away from me. Okay, I got it. So the toric multi-axis, what we're doing is we're contouring the flat and steep meridians. You can see by these post-wear maps that we have flat periphery, steeper here, and the toric design has molded that cornea into a nice fit. So using the toric treatment zone, we can even get rid of lenticular or residual astigmatism. So that covers the toric designs as far as an introduction goes. And the toric designs are a lot easier to fit than people think. They really do the work themselves. So if we get good data, I think you can get good results with those. So now we'll go into the myopia control designs and why we need those. You know, Earl Smith showed, it's been 2008 or 12, a long time ago, that hyperopic defocus can stop the progression of myopia. And traditional Ortho-k designs work sometimes, but then sometimes they didn't work. They didn't stop the myopic progression, and none of us understood why. Now we know that it has to do with pupil size and treatment zone size. So that's the reason that we need these myopia control designs versus straight Ortho-k. So this slide shows you an Ortho-k lens for what I call myopia reduction or straight orthokeratology, and you can see the large treatment zone compared to in the bottom picture. This is a lens for myopia control where we have a much smaller treatment zone, a wider reverse zone to build up the tissue so that we have a buildup of plus power that causes that peripheral defocus. You can see here, we're looking at a myopic cornea where the focal point is not hitting the back of the retina, a hyperopic defocus where it's too far, and what we're trying to do, we saw the Lorick study, which was a very small study, but we monitored the axial length and the chamber diameter in these patients. You can see that the control group, over 2 years, the axial length increased 0.48 millimeters, which is significant. With Ortho-k, and this was done without the myopia control designs. So you can imagine a newer study would be even better than this, but it's 0.23 millimeters over 2 years after Ortho-k. So this slide right here is the most important reason that you have a responsibility to do Ortho-k on your patients, or at least do myopia management so that these children, their eyes don't get worse, that you can stop them from getting worse. The myopia control designs, I call it pediatric Ortho-k. It's really a lot different than the traditional designs, which I call adult Ortho-k, larger optic zones. And I think Chandra touched on the subject that, you know, we want to, once a patient is driving, they really need to be in the bigger optic zone design so that they don't get glare and flare at night. So it's best to start Ortho-k or myopia control on kids when they're very young. It's best to start even once they're a -1, -0.5, especially if they have a history of Ortho-k. You really want to start them young so that you can stop the myopia before they turn into a -4. once they become a -4, that's always going to be their baseline for the myopia. You won't be able to hold them at -1. So that's a concept that's a little hard to understand and accept, but the sooner you start doing Ortho-k on the kids, the better off it is for them. And here again, I'm showing the traditional Ortho-k with a very large treatment zone and a myopia control Ortho-k with a very small treatment zone. One of the things that we do with myopia control Ortho-k is that we have a double reverse zone. We use 2 reverse curves. The first reverse curve builds up the plus power. So we've got the optic zone, and then reverse zone 1 is much steeper than reverse zone 2, so that we can build up that +4 hyperoptic blur to cause that peripheral defocus, which keeps the muscles contracted, so that the patient doesn't get worse and the axial length doesn't increase. So on our OKEX design, which is really what we're talking about with myopia control, we use aspheric treatment zones. So with an aspheric treatment zone, if you have a 9mm radius in the center, by the time you get to the edge of the optic zone, that radius might flatten all the way to 9.8mm, depending on what eccentricity value is used. And what that aspheric treatment zone does is it causes the lens to lift off the cornea further, so that we build up more plus on the patient's peripheral area. The reverse zone 1 that creates the +4 peripheral defocus is an optical curve. It must be optical in order to create the defocus. There are other designs out there where the reverse zone is not optical. For example, a sigmoid curve does not produce optics. So it needs to be a curve that is built on the optical center of the eye, in order for you to have clear optics for the defocus, if that makes sense. Myopic control lenses, they really fit the same. They're not that different than fitting a standard orthokeratology design. They do need to fit a little bit tighter, a little more snug, in order to build up the +4 tissue. So that's something that you have a little adjustment. With standard orthokeratology, we really want the lens to fit a little looser, have a nice tear film, and allow the patient, when they blink, the lens should move a little bit. Whereas with myopia control Ortho-k, we still need it to fit safely and not too tight, but a little less movement, about 1 millimeter of movement. Myopia control Ortho-k, you're going to have a smaller treatment zone, but you're going to have a very wide reverse zone because of that big, brilliant pooling, that wider area to build up the plus. As Chandra mentioned, when you're doing myopia control, it's important to measure the optic zone of the pupil diameter, so that we can determine the best optic zone for those patients. Now, we have found by fitting lots of myopia control lenses that 5.4 millimeters is the best average optic zone. It seems to create the plus right outside the pupil, and as you can see, boys will have a larger pupil than girls. So sometimes with boys you might need a 5.6 or 5.8, but girls have a little smaller. My rule of thumb is that the optic zone should be 0.2 millimeters larger than the pupil. Some doctors fit it smaller than the pupil to try to get the peripheral defocus, but that's when patients complain about blur, and even the kids will complain if the optic zone is too small. So I think 0.2 millimeters larger than the pupil. Here's a myopia control post-wear topography. You can see that the treatment zone is very small and the steep ring is very close to the pupil. So this patient is getting a very good peripheral defocus just outside of the pupil zone. So now I'm going to cover parts about the OKEX design, which is the myopia control Ortho-k design. We use the hyperbolic treatment zones, which is aspheric, and a double optical reverse zone. The lens also has a double aspheric alignment zone, and we can use larger custom size diameters with this design. I've covered this hyperbolic toric curve, so we won't get into that, but all of our designs can be made toric. This is more about the fluorescein pattern. This is a lens right at dispensing, and you can see the bubble in that first reverse zone. It's very deep. It's so deep that there's some bubbles in there. Once this lens starts to mold the cornea, those bubbles will dissipate, and you can actually use a drop in the lens to try to reduce those bubbles. This again is upon dispensing with a higher myope showing that bubble again, and that's in order to build up that peripheral defocus. This shows a loose lens. You can see it breaking away up top here, and the central treatment zone is much smaller. So this lens, you would need to tighten it up a little bit to get a better fitting lens. This is an example of a tight fit. You can see that there's a little bit of edge lift out here, but the alignment zone is very dark compared to the central treatment zone. You always want your central treatment zone and alignment zone to be similar, or if anything, the central zone should be darker, have more touch. So that really summarizes the OKE